Have you ever seen a water droplet seemingly dance and glide across a super hot pan, appearing to defy immediate evaporation? Or perhaps watched a small bead of liquid nitrogen roll around without boiling away instantly? This intriguing behavior is not magic, it is physics in action. That fascinating phenomenon is thanks to the Leidenfrost vapor layer, which forms an insulating cushion, temporarily protecting the liquid from extreme heat. Its primary purpose is to create a thermal barrier between a liquid and a surface that is much hotter than the liquid's boiling point, significantly slowing down evaporation. When a liquid encounters a surface significantly above its boiling point, the part of the liquid closest to the hot surface rapidly vaporizes. This sudden burst of vapor creates a thin, protective gas layer beneath the main body of the liquid. This vapor layer acts like a cushion of steam, drastically reducing the heat transfer from the hot surface to the liquid above it. Because the liquid is floating on its own vapor, it never directly touches the superheated surface, which would cause it to boil away much faster. This insulating effect is so strong that it allows the liquid to persist for a surprisingly long time before fully evaporating, essentially preventing rapid boiling by maintaining separation. This principle is actually quite useful in various practical applications and everyday observations. For instance, it explains why a skilled chef can flick water onto a hot pan to test its temperature. If the water forms beads that skate around, the pan is hot enough to exhibit the Leidenfrost effect. If it just sizzles and evaporates quickly, the pan is not yet at the required temperature. It also plays a role in some industrial processes where very hot materials are handled, providing a temporary buffer against extreme temperatures. The critical temperature at which this effect begins, known as the Leidenfrost point, can be hundreds of degrees Celsius above the liquid's boiling point, which is why the effect is so dramatic. For water on a steel surface, this point can be around 100 degrees Celsius or 400 degrees Fahrenheit. This specific temperature threshold ensures that enough vapor is generated rapidly to form and sustain the protective layer, a clever trick of thermodynamics. Understanding the Leidenfrost vapor layer reveals a hidden protective mechanism in nature, showing how a simple phase change can create an effective insulating barrier. This vapor cushion allows liquids to temporarily exist on surfaces for hotter than their boiling points, offering us both a fascinating visual spectacle and a valuable scientific insight into heat transfer and fluid dynamics.